All right, today we're going to dive into a really strange rule in physics. It basically says that you can never, ever truly know everything about something, no matter how hard you try. Yeah, you heard that right. It's a fundamental limit on what we can know, and it runs the entire quantum world. It's called the Heisenberg Uncertainty Principle.
Okay, so let's start with a question that seems, well, almost ridiculously simple. Imagine you've got a cricket ball flying through the air. Can you know exactly where it is and exactly how fast it's moving at the very same moment? I mean, in our everyday world, the answer feels like a clear, duh, of course. But what happens if we shrink that ball down, way, way down, to the size of a single electron? Is the answer still so simple?
And this is where reality just takes a bizarre left turn. Because quantum physics looks at that very same question and gives a hard, definitive, and kind of shocking answer. No. It's not just difficult, it's fundamentally impossible. And listen, this isn't about us not having good enough tools. It's a basic, unbreakable rule of the universe itself. So this shocking idea has a name, the Heisenberg Uncertainty Principle. So who on earth came up with a rule that seems to fly in the face of all common sense? Well, that would be the brilliant German physicist Werner Heisenberg. Back in 1927, he dropped this idea on the world. And it wasn't just some small adjustment to physics. No, this was a full-blown revolution. It completely upended how we understand reality at its most fundamental level. So what does this principle actually say, and how do you even write it down? Let's get into the formal definition and see how this all builds up into a really powerful mathematical idea. Okay, here's the official version. It says you simply cannot know both the exact position and the exact momentum of a particle at the same time. Think of it like a cosmic seesaw. The more you pin down its exact location, the more its momentum gets all fuzzy and unknown. And if you somehow manage to measure its momentum perfectly, well, then its location becomes a total mystery. You can have one or the other, but you can't have both perfectly. And this little equation right here, this is that whole idea captured perfectly in the language of math. See, this isn't just some vague philosophy, it is a hard limit that's literally baked into the fabric of the universe. It tells us that the uncertainty in position multiplied by the uncertainty in momentum can never, ever equal zero. It always has to be bigger than some tiny specific number. So let's quickly break that down. That little triangle, delta x, that's your uncertainty in position, how fuzzy its awareness is. Delta p is the uncertainty in its momentum. And that h, that's a little thing called Planck's constant. It's a super tiny, kind of mysterious number that is the whole key to why this rule really only matters on the smallest scales. We're definitely coming back to that. But why? Why does this weird trade-off even exist? Well, the reason is just as fascinating as the principle itself. And it all comes down to the simple act of, well, looking at something. Let's walk through this together. Imagine you want to see an electron. To see something that small, you have to hit it with something, right? In this case, we'd use a particle of light, a photon. Now, to get a really precise measurement of its position, you need a very high-energy photon. But here's the catch. When that super energetic photon smacks into that tiny little electron, it's not a gentle tap, it's a huge collision that sends the electron careening off in a new direction, completely changing its melenging. So here's the mind-blowing takeaway. At the quantum level, you can't just be a passive observer. The very act of measuring something fundamentally changes it. By finding out where the electron is, you've completely messed up where it's going. You aren't just watching the experiment. Your observation is an interaction that actually alters reality. Wild, right? Okay, this brings up a really obvious question. If this is all true, why don't I notice it when I'm watching a car drive by or that cricket ball from earlier? Why does the physics we're used to work so perfectly in our big everyday world? The secret is that little h from our equation, Planck's constant. Just look at that number. It's so ridiculously small. It's a decimal point followed by 33 zeros before you even get to the 6. For all practical purposes, it's 0, but it's not quite. And that not quite makes all the difference in the universe. So let's put it side by side. When you shine a light on a huge cricket ball to see it, the effect of those photons bouncing off is so tiny it's completely negligible. The uncertainty it creates is effectively 0. But for an almost massless electron, that same little photon interaction is a total game changer. The uncertainty isn't just big, it's a fundamental, unavoidable part of its reality. So you can see this isn't just some weird little quirk of the universe. The uncertainty principle is an absolute cornerstone of modern physics, and its implications are, well, they're profound.
So why does this matter so much? Well, for starters, it completely destroys the old idea of a predictable, clockwork universe. You can't perfectly predict a particle's future because you can't even perfectly know its present. This means that at its very core, nature doesn't deal in certainties, it deals in probabilities. It's a universe of maybes and probablys, not definitelys.
To put it simply, the uncertainty principle isn't just part of quantum mechanics. It's one of the pillars the entire theory is built on. You take it away, and the whole thing comes crashing down. And believe it or not, this isn't just abstract theoretical stuff. This principle is the reason atoms are stable, why electrons don't just spiral down into the nucleus. It's also the foundation for a super weird effect called quantum tunneling, which is essential for everything from how our sun works to the transistors in your computer. So, we end on this thought. The uncertainty principle isn't just about tiny particles. It forces us to ask some really deep questions about knowledge and reality itself. If the very foundation of our universe is built on uncertainty, where perfect knowledge is literally impossible, what can we ever truly know for sure?